So in this lecture, we will continue with classical chaos and try to finish it to the extent that we can start with quantum next time. And last time, we basically set up the stage for non-integrable systems by describing what are integrable systems. And just to recap, integrable systems are those in which you have n degrees of freedom and n constants of motion, which are all independent, and in some sense they are special. And essentially you can have some action angle variables which are able to describe the system, which means that all these n actions are constants of motion. And the angles, therefore the n angles form a n torus. And the simplest and non-trivial example, of course, the one-dimensional case is always integrable because there's one constant of motion, namely energy. When you go to 2 degrees of freedom, that's not the case. So you have non-integrable systems in 2 degrees of freedom. But for integrable systems, you have 2 constants of motion, energy and something else. And and there are 2 angles, and therefore we can actually visualize this torus as the usual tube topology or Medu-Vada topology. And phase space is kind of foliated by this. But let me also warn you that the picture is not that simple, as we will come by, as we will say that any given energy, at a given energy, you have an infinity of these tori. It's not like in one dimension we have too much of our background from 1 degree of freedom, where typically you have one energy and one torus or one closed loop. But that's not the case once you go to more than 1 degree of freedom. So, and we also introduced these rational tori and irrational tori when the frequencies of motion on these tori are commensurate, they are rational, and when they are incommensurate, they are irrational. And these two have very different fate when you start introducing non-integrability. So that's what we will do today. So this is the setting of I've just stated the KAM theorem. It's not essential that we understand every single part of it, but the essence of it hopefully gets through. So we have here this I is just to indicate all n possible actions. So you have an integrable system, which is a function only of these n actions. And then you have a perturbation which includes the angles, so that it's no more integrable, H is no more an integrable system. So the topology of this I are real numbers, and theta are angles, so this is the n torus. H0 is integrable, epsilon is a small perturbation. We are going to leave that open, what exactly we mean by small. But it's clear that in some sense this term here is much smaller than the energy of the integrable system. And suppose that H0 leads to these frequencies, that is the unperturbed tori have these frequencies, then they are non-degenerate. That is that the frequencies are determined by the actions and vice versa. The Jacobian of this frequency with the action is not equal to 0. The determinant of that is not equal to 0. So those are the conditions of the KAM theorem. Furthermore, it says that there are certain tori which are stable. They don't break up immediately on this perturbation. And those tori are those which are sufficiently non-resonant. It's not sufficient that they be non-resonant. They should be sufficiently non-resonant in the sense that they should be sufficiently irrational. These frequencies, for example, if you just think of 2 degrees of freedom, there's only a ratio of these frequencies. The ratio of these frequencies has to be irrational for it to be an irrational tori. Remember the pictures that we had, it should be like this. It should be winding around indefinitely on this, and this frequency should be rational. And not only that, this irrational number must be sufficiently irrational. And there is a whole theory of how close to rational numbers irrational numbers are. and there is a hierarchy of them, and you can always approximate irrational numbers by rational numbers. The larger the denominator is, the closer you can get to the irrational number. So for a given denominator, the question is what fractions are the ones which are most close to the irrational number. So in that sense, these things are called Diophantine conditions. They've been studied by mathematicians, and the condition for the KAM theorem is that this combination omega dot k, remember k is all integers except all zeros, not everything can be zero. So omega dot k should be larger than something which goes as 1 over k to the power of something. Okay, this k is these integers which are going into this. So this is a lower bound on this product. This cannot go to 0. If it goes to 0, then it's a resonant torus. So you not only want it to be irresonant, or non-resonant, but you want it to be sufficiently non-resonant in this sense. And this tau can be related also to the number of degrees of freedom that you have. So for n equals 2, this has to go as gamma of modulus of k. So you consider only non-resonant tori of this kind. And it turns out that actually these kind of non-resonant tori are numerous. It's not that they are actually of measure 1. So they are. It's not that they are very rare, and therefore these are the unperturbed frequency conditions. Then KAM asserts that for sufficiently small perturbation strength, the corresponding invariant tori persist under perturbation up to a deformation. They are not like it's exactly the same. They just twist around a little bit. They deform. So this is the condition of the KAM theorem. It says that sufficiently irrational tori survive. Yeah. Can I ask if you don't mind if you were there in the last lecture? Yeah. Okay. So the resonant is this when the ratio of these frequencies is a rational number. If you have two frequencies, if you have more than two frequencies, if you have some integers such that omega j, kj are integers is equal to 0, then you call that resonant. Those set of frequencies resonant. It's a commensurate condition. These frequencies will be commensurate. So yeah. So tori with that are called resonant tori or rational tori, and those which are not of this kind are irrational tori and non-resonant. Please do ask me, doesn't matter if this is something which has been mentioned, please do clarify, otherwise it will not be much use. Yeah. So what determines the threshold? Irrational enough condition, what determines the threshold? This is the condition. So what determines gamma? Gamma is just some constant. So if there exists some gamma, tau is kind of bounded by the number of degrees of freedom. As long as you have gamma and tau. So any gamma greater than 0? Yeah. If you have those things then it's fine. Like for instance, let me tell you right away, and you will see evidence of that. The most irrational number, so it goes. So the lower goes is the golden mean. The golden mean is the most irrational number because it is the most. Its rational approximations are the worst possible. We'll come to that. Okay. Yeah. All right. Good. So now, as we are stepping into more than 2 degrees of yeah, Sanjeev.
Tau depends on the set of case you choose, right? Or
no. This gamma and tau have to be independent of k. This has to be true for all k.
All choices of
all, yeah.
Tau and gamma, 6.
Yeah, Yeah, that should exist for some constant gamma and tau for all k.
It depends on what, because I guess for different system it will be different, right? Tau and gamma. Is there some kind of universality of tau and gamma?
Not depending on systems, it will depend on your set of frequencies, which would then you can say depend on the system. Like for example, suppose you take 1 and root 2. It can have a different gamma and tau than, say, square frequencies, yeah, omega.
So when we say that invariant torus persists, so what does it mean? In fact, so these i's are conserved quantities, right?
Yeah.
The absence of epsilon. So are you saying some of those conserved quantities remain conserved?
Yeah, there will be still conserved quantities. So what you will be trying to do is to do some perturbation expansion. That's really what Poincaré, everybody else was trying to do, so that this itself goes to an action angle variable. So now I and theta are not good action angles. So you'll do a perturbation of that and try to see if you can eliminate theta to whatever order. Now suppose you were able to find a new action such that it is a function only of the new action plus epsilon square something, which now can depend on the angle also. You have postponed, you have done better. And that you try to do infinite number of times. Yeah.
So I get that the mathematics that you are using to say that the rational tori vanish.
Sorry?
So you are saying that the irresonant tori
persist and the resonant tori just go vanish. But can you...
Not that they vanish, they get destroyed.
Yeah, they get destroyed. But can you give like an intuitive example of how they vanished? Like you start up the perturbation.
I will come to that.
Okay, sure.
This is the mathematics, but that's why I'm using a computer, so that I can visualize. Yeah. Yeah, partly, certainly. Also, by the way, I mean, here this is not the KAM theorem, look at this. It's a real analytic Hamiltonian. So that means that H1 must be differentiable a whole lot of times. Okay? So infinite number of times if it's analytic. But there are softer versions. Moser proved a version of the theorem, which we will come to, at least the setting of the theorem, in which he only required it to be differentiable 333 times. Okay? And then later on, it was decreased to many times. But I can assure you that if it is not even differentiable, then the theorem is not correct. You can have continuous but not differentiable. You could have a situation where these tori break up even if they are irrational. There is a lot of subtleties, but this is the basic point which I want to convey.
here all tori persists, right? Stays.
Almost, a lot of tori persist because of this. Almost all tori, if you wish, because they are, almost all numbers are irrational in some sense. And so you'll have a dense set of irrational tori which persists. Again, I'll show you pictures. Okay, so I want to show you pictures, but for that, maybe I will, yeah, okay. I'm going to introduce Poincaré service of sections here. My ordering might be slightly off, but nevertheless, let's go back from theorems and let's see what we can do ourselves without the help of KANN. So we have gone from 2 degrees, we have gone from 1 degree of freedom, and we could plot all those phase spaces, which we saw last time, to 2 degrees of freedom. The dimension of the phase space is 4, and we are sunk. We can't visualize 4-dimensional phase space. That's a pity. Even 2 degrees of freedom, we cannot visualize. We are 3-dimensional creatures. But Poincaré realized that you can still visualize 2 degrees of freedom usefully in just 2 dimensions, because 4-dimensional phase space, but it's Hamiltonian, so you have energy to be conserved. So you have one constant of motion. So let's fix the energy E. and consider all those x, y, px, py such that this condition holds. You're given some Hamiltonian, okay? These are the 2 degrees of freedom, x, y, and the corresponding momenta. Now, this describes the 3-dimensional subspace of this 4-dimensional phase space, that is a fixed energy shell. We usually call in physics energy shell, okay? But actually we don't understand the complexity of this object. Even for something as simple as uncoupled harmonic oscillators, this is the 4 sphere. So it's a very interesting geometric object. So now let us choose an energy E, as I said, and choose initial conditions, x0, so the 0 denotes time here, initial conditions such that this is having some energy E. Now then we go to the computer and ask it to solve. If you can solve it, fine. And you find out all the x of t, y of t, px of t, and py of t. You solve the equations of motion, Hamilton's equations of motion for the orbit in phase space. Now this is lying, it's a 4-dimensional orbit restricted to this 3-dimensional manifold. But now there exists a sequence of times, t1, etc., t1, t2, etc., where there is a special condition which is satisfied. Let's say this coordinate y goes to 0. Okay? It's crossing the y-axis. Y of tk equals 0, and we will also require that the momentum at that point be greater than 0. Okay? It can be negative, but we are going to not look at when it's negative. We are going to look only at those sequence of times when y is 0 and the corresponding momentum is positive. Y is crossing from negative to positive, so that py is increasing. So then the Poincaré surface of section is a discrete set of points, that is this x and px evaluated at these times tk. So I will just denote, I won't write tk and all this, I'll just write xk pk. Okay, so that is the definition of Poincaré surface of section, and the map itself, the Poincaré map, is a map which is relating xk pk to k plus 1 pk plus 1. So the next time it's going to satisfy that condition, there exists a map which will be connecting this. Now you see it's a discrete time system. We are connecting discrete variables at 2 discrete time steps. Okay, it's not a differential equation, it will be some difference equation which is relating this. And it turns out, and this is not something which is trivial, it needs a proof from fairly advanced classical mechanics, that this map is area preserving. I will tell you in a minute what I mean by that, but it's not any old map, it preserves areas on the map. So, okay, so here I go. Let's try to visualize this for a 2-dimensional uncoupled harmonic oscillator. The first one here has rational frequency, so any orbit will have a periodic orbit. It will be a periodic orbit. What have I marked here? Oh, okay, this is the trajectory in space. This is what I think we call Lissajous figures or something like that. X versus Y. Okay, so it's crossing and all that. But we don't want that. We want 4-dimensional phase space. So whenever it is crossing, maybe I started, I don't know whether I should start it again. So whenever it is crossing y equal to 0, you see there is a point which is marked here, and then there is a point which comes here. So this surface of section, this is now the surface of section, x versus px, whenever y is crossing 0 and px is positive, it's putting this. So this entire y is 0.
No, py is positive.
Py is positive. So like for instance, now it will mark, but not now. Okay. So when it's going down, it won't mark it. While it's going up, it will mark it. You don't see that from this because it's marking, but you don't see it because it's the same point. Okay. It's a periodic orbit. You can see that this entire orbit is really 3 points on this surface of section. And it is a periodic orbit on the surface of section. It will go from here to here to here. It will just keep doing this, hopping between this to this. So we will go from continuous flows to these discrete maps. So actually maybe the irrational case we can see for more. So yeah, so now it's crossed y, so now it's gone. It's crossed y but it's gone negative, now it's gone, come again. So whenever it is crossing y equal to 0, that is this thing here, and it's going up, the red dot is going up, you will mark x, which is this this direction, and the momentum in that direction. Okay. What sort of closed curve will you get here? So this would be called a quasi-periodic. It doesn't repeat. It's not periodic. It's quasi-periodic. Its frequencies are incommensurate. And the object here will be, in this case, it looks like a circle. In general, it will be an ellipse. Okay. Probably here also it's an ellipse. It's only a matter of the scaling in this. So this is a Poincaré surface of section, and this, therefore, this rather complicated orbit has a simple form in the surface of section, and we can visualize 2 degrees of freedom systems using a 2-dimensional map of this type. So now let's do more serious things than harmonic oscillators. So here we have a quartic oscillator to the power 4, and then it's coupled also like this. Now if this is a 2 degree of freedom system, it has 2 parameters, alpha and gamma, and this can be integrable only in these 3 cases. It's known to be integrable only in these 3 cases. Gamma is 0, that's trivial because it's separable immediately, and there are 2 energies, independent energies, that are constants of motion. When alpha equals gamma, why is it integrable? Yeah, you can complete the square, so it's q1 squared plus q2 squared whole squared, and therefore there is a rotational symmetry. There is a rotational symmetry, q1 plus q squared, q2 whole squared, q1 squared plus q2 squared, so it doesn't depend on the angle, so there's angular momentum is conserved, and alpha equals gamma is integrable. The other case is alpha equals gamma by 3, and that you can see is separable if you do a 45-degree rotation. Okay, there are only these 3 cases when it's integrable. So in fact, here is a case, the surface of section, which is q2 equal to 0, the 2nd degree of freedom, I called it y in the last slide, now it's q2, equal to 0, momentum is positive. Okay, and you're plotting q1 and p1 whenever this condition is true, and all this is for a given energy. In this system, it's a homogeneous system, and all the Poincaré surfaces of section at all energies look the same. They will just be scaled versions of each other. So there's no low energy versus high energy. So it doesn't matter what the energy is. I haven't even mentioned it. Any energy you take, and fix, let's say, this gamma to be 1. Okay. The first case here is when alpha is 1/3, which corresponds, you can see, to this integrable case. So you now see here the tori, which I talked about. These are irrational tori typically, because you're now seeing many, many points. They are similar to what we saw in the last slide for the irrational case. Okay, and you also have some fixed points at the center, and you also have a case where you can have a rational torus also in this case. So now this is the case when alpha is 1/3 integrable. So this is now decreasing alpha away from 1/3 0.28. You can see immediately that the phase space is quite different. Now you can see that if you think of these as tori, it's been perturbed, it's been sufficiently perturbed enough that there are some which are distorting. It's not very small. So you're seeing actually already quite a bit of distortion, but you can think of these tori as deforming into some of these tori. Yeah. And then there are rational tori, which you don't see, which are, on this picture, you don't see that clearly. They are breaking up and giving rise to these interesting structures. We'll come to such structures in other pictures. And then you have the secondary islands and so on. So this is already a fairly complex picture of a non-integrable system where you have a fair amount of stable orbits, such as these, and these KM tori which are surviving these perturbations. So they will be just called KM tori when this. You can see that as alpha is decreased slightly, it's not very drastic, by the way. It's 1/3 to 0.25. You can see a very drastic change in the surface of section. The KM tori seem to have already been almost destroyed. You have these platter of points which you're seeing. So you have still very complicated tori structures here, but they are not simple tori. And you have this platter of points, which is actually the genesis of chaos. And here is a case of 0.166 alpha. And what is plotted here is a single orbit. Okay, so here there are multiple orbits, multiple initial conditions with the same energy. Here it's a single orbit, and you can see that it's already covering pretty much the entire allowed surface of section. It can't go beyond this because of energy constraints. So it's excluding some regions here, which clearly involve some kind of regular orbits. I'll call these things regular orbits if they are stable or orbits. And then these are what we will call chaotic orbits, which are coming here. So in fact, if alpha is 0, that seems to be the small, as we are decreasing, the chaos is increasing. If alpha is 0, it seems like a very simple potential where you have simply q1 squared, q2 squared, x squared, y squared potential. This is one of those potentials that fascinated a lot of people. For a while, people thought this was completely chaotic. That is, here you have some initial conditions which are not chaotic. But this one, if you do the phase space, and I encourage you to do it if you haven't, so that you can learn these things better by doing it, you will find that this is almost fully chaotic. But then people did find very small islands of regularity in this as well. And there are other interesting aspects to this. Its quantum mechanics is very interesting because there is one orbit which is scattering. If you start from Q2 equal to 0 and P2 equal to 0, it will always remain on Q1 equal to 0. I mean, it will always remain on the Q1 axis. So you're putting all the energy into one of the oscillators, but then it's scattering, so it goes off to infinity. But it still has bound states. All the eigenvalues are bound states. I'm already starting to talk quantum mechanics, but in fact, these kind of systems were studied intensely so as to understand the quantum mechanics of this. So this is from this reference, is from this physics report early on, quantum mechanics of classically non-integrable systems. Okay.
You're just plotting xk pk.
Yeah, exactly. xk pk. Whenever y is 0 and py is larger than 0.
But the figures, the bigger one which is implement.
Which one? This one you mean?
Yeah, implement the bigger one is there.
Yeah. So that one will correspond to the case where all the energy is in the Q1 P1 plane. So you can have this balance of energies, right? So you could start with something which Q2 is 0 and P2 is 0. So you can think about this as an extreme orbit of that kind. So in fact, this will be actually a quartic oscillator, not even a section, because you see, what is a section? Section and orbit has to come, intersect and go out. So it has to transversely intersect. Here it will not be transversely intersecting as you're getting close to this, because if it is Q2 is 0 and P2 is 0, it's always going to be Q2 is 0. Huh?
Because I thought you excluded that, right?
No, Q2 is 0, P2 is 0. So this will be, strictly speaking, excluded because P2 is greater than 0.
P2 is 0 plus.
Yeah, P2 is 0 plus. So they will be approaching it very closely. Yeah. Why chaos does not enter into this regular region? why it does not penetrate that. That's the nature of the orbit, but as we are going by, you will see more. It has to do with the fact that it's a it's a three-dimensional space in which you have these tori, so they are acting as barriers. Again, you don't have, you can't have trajectories crossing. So that is prohibiting this. This one is not a continuous trajectory. I must warn you that these are maps, right? So it's jumping from one to the other. Two-dimensional flows, we said, are simple. This is a two-dimensional map, far from simple. Yet there is that restriction which does not allow this to penetrate. But it's very interesting that when you go to 3 degrees of freedom, what will be the surface of section's dimension? It now becomes 4-dimensional surface of section. Already the map is 4-dimensional, and there these tori, they don't separate out. So you can have it's a new phenomenon there called Arnold diffusion, which is present in 3 degrees of freedom, not in 2, where you might have things like that going on, where something is going from an integrable region to another integrable region through some chaos and things. So it gets more interesting also, and difficult. Of course, yeah. Not by chance. Unless you take it, it will not be by chance. I'm not going to take it to be complex. For me, this is complex enough.
These points, they appear in some order or they come in
It depends. Like we will see. I will show you. I'll show you actually in real time, but not for this. For another system.
like, for example, the simpler one, like the previous one.
Yeah, simplest one. There will be an.
The previous one where it comes in a circle. Just the previous cluster. Was it coming in some
No, it's
order?
not coming at the base regularly, it's coming.
Yeah, it will. It will.
Is it
Yeah.
random or maybe is it a good random number generator or?
No, not a good random number generator because it's basically quasi-periodic still. So not a good random. But the chaotic part, of course, is a good random number generator. Yeah, sure.
Yeah, just a comment, so if I start from the center in the regular region, then it's just the converse of Q2 and Q2 being 0. Right? So if P1 and P1 being 0, then they have to stay 0 always. And so that's why starting from the center, I cannot move out. Is that one way to understand?
Yeah. So this is a fixed point there. Absolutely. So that is Q1, P1 equal to 0. And then you're waiting to see when Q2, P2 is 0. So it's got to be, that is, yeah. So this one will always be, because you have put all the energy now into the other degree of freedom, Q2, P2. Yeah. So that's a fixed point.
But again, that is not allowed for, otherwise, in Q2 is 0, so all energy only will be on momentum, E2. Because that point, so it's so all momentum, so all energy has to be on P2 only, right? Because all these plots are also with Q2 0.
Q2 is 0. So everything becomes kinetic. Yeah. Yeah. Huh?
P2 square, there is a typo.
Where is it? Oh, yeah. Thanks. Yes, please. I mean, P1 square plus P2 square. Good question. Good question. Do it and see. Good question. Do it and see. Also think about why is this restriction P2 greater than 0, but actually in this case that will help. P2 not being, but in general it will not help. In this case actually you will get twice for the price of 1 because of symmetries.
So you said the center is a fixed point. But does a fixed point necessarily imply that there will be a regular region around it, or there is no such?
It's not required. So it depends on the nature of that fixed point. It can be an unstable fixed point. But maybe some of those things, see this model is still too complicated for me. I'll have to simplify.
So is it like you have chosen, you have one section where some values of Q and some values of Q. So is it chosen all choices of, I could have chosen some other choices of Q2 and some P2.
Yeah.
I will get a similar.
Yeah. So
it's independent.
there is nothing sacred about this surface of section.
Yeah.
You can take other surfaces of section. In fact, you may be, because you're relying on a set of orbits to intersect a section, so you would like all your orbits to intersect that section, but maybe some of them don't, So actually, maybe you can visualize this much more easily just in 2D flows, because 2D flows are simple enough, as we said. 2D flows, you can take a section by drawing a curve and seeing when it's crossing that curve. You will get a one-dimensional map out of that, okay? So, in fact, we will come to one-dimensional maps. So, so you can alter these things. Ideally, if your sections are good and orbits are intersecting transversely, these sections are related by some smooth transformation. So if you have one periodic orbit, you'll have the same periodic orbit there, just a transformation on that. If it is stable, it will be stable there. There'll be homomorphic or homeomorphic. There'll be some homeomorphism connecting them. Okay, good. So we'll move to other systems. I just want to show you there is this famous class of problem which is just free particle, but now in 2 dimensions. So we all study particle in a box in quantum mechanics. This is particle in 2-dimensional boxes. They can come in various sizes and shapes. So these simplest ones, a particle in a circular billiard, and a rectangular billiard in general, elliptic billiard. Practically speaking, smooth shapes, or actually shapes itself, apart from a few triangles, like an equilateral, these are the only known ones which are integrable. Okay, so you have just a free particle bouncing here. You can think about it like a ray of light. Reflection angle is equal to incidence angle. Okay, you keep playing this game. At any point it intersects, draw a normal, and then angle of incidence equals angle of reflection. Now, why is this particle in a circular billiard integrable? It's got 2 degrees of freedom, x and y. It has to have 2 constants of motion. One is the energy, which in this case would be just the velocity squared, bx squared, because it's just free particle. Kinetic energy is all that's there. Angular momentum, very good. Angular momentum is conserved. Here, why is this integral? Huh? 90 degree doesn't help, unfortunately. Discrete symmetries don't lead to constants. But why is a rectangle? Huh? That is kinetic energy. I mean, that's the total energy, because there's no potential in this case. P1 and P2 are? No. You're almost there, but not quite, because when it's encountering a wall, if P1, P2 are constant, it's free particle. Almost free, but except at the border. So now refine it, mod P. So P1 square and P2 squared are independently constants. Okay, so it's like separable. So that's why this is, what about this? Ellipse. Ellipse is a very interesting, non-trivial example. It doesn't have circular symmetry, so it's not immediately clear that angular momentum is this thing, and then it's not separable like this one is separable. But it turns out, and this is a good exercise for students, that if you calculate the product of the angular momentum about the 2 foci, that's a constant. And it comes from the property of the ellipse, if you think about it a bit, that anything that goes through any trajectory that passes through one foci has to go through the other foci. Okay, so the product of the angular momentum about these 2 foci is a constant, turns out that that's integrable, but you do pretty much anything else to these shapes, it becomes non-integrable. So you can take a square like this, put a circular thing in between so that things are bouncing off the circle. Then this is called a Sinai billiard after Yaji Sinai, who showed that actually this is a fully chaotic situation. So that is how the trajectories evolve. This is another named after another bunch of Russians, but otherwise called stadium billiard. It's also called the Bunimovich billiard, which consists of straight line segments like this, and then semicircles attached to this, semicircular caps. So it looks like a stadium. And this is also an example of a fully chaotic thing. This is an interesting example. It's called a limacon or limason. I don't know how to pronounce it. But this is r equals constant. Now let us distort the circle, 1 plus epsilon cos theta. If epsilon is 0, that's integrable. If epsilon is not 0, this becomes then near integrable. You can expect epsilon equals very small. You can expect KM theorem to hold. And then when epsilon is large, things can break down. In fact, when epsilon is 1, that is the cardioid shape, and it looks like this, and it's fully chaotic, again like this. That means that there is no, it's proven mathematically, there's no island of stability anywhere in this. And all of these, they're all homogeneous, so it doesn't matter what energy these particles have. So now here the surface of section is, which one? First is this one?
So there is no boundary in section.
No.
So if I put the boundary, it's still integrable. If I put circular boundary, it looks like a boundary.
Yeah, good question. By the way, this is not a boundary, as you said. This is called a caustic. When you look in a teacup, you will see bright patterns, which is coming from light rays balancing and pointing. Most likely, it looks like a cardioid shape when you look at your teacup. This one is a caustic. Okay, so all these rays are having this. they are tangent to this curve. But your question is, if you put a circular thing here, what do you think will happen? Oh, why should it still? Angular momentum is still a constant. Okay, so you can put, and how will you break that? No. Still with a circle, how will you break it? Concentric. Shift the center of that circle away, chaos will set in. It becomes non-integrable. Potentially, chaos will set in. It becomes non-integrable. People have played with all kinds of billiards. There are very interesting problems in billiards, both classical and quantum mechanics. Okay, so this is a surface of section for the limacon billiard at some epsilon is 0.3, I think. I haven't written that here. My collaborator, Arne Bakker, has done a lot of work on this limacon billiard. You can look at his website and his papers in TU Dresden. So what is the surface of section for billiards? So there is a particular coordinate, in fact studied by Birkhoff himself, and they're called Birkhoff coordinates. You can take one of the coordinates to be the length along a perimeter, because all you need to be interested in is where it is colliding with the boundary of the billiard. Otherwise, the dynamics is simple, it's a free particle. So you will want to monitor the consecutive collisions with the boundary wall. So when it is hitting the boundary wall, you ask where is it hitting and what is the velocity with which it is hitting that? What is the speed along the tangent, tangential direction, the speed. These two form a canonically conjugate pair. You can prove that they form a canonically conjugate pair, and the plot of that is this kind of a picture. And you can see again, it's a bit like that case which I showed you of the quartic oscillator, that this blue will be a single orbit. It can be moving around randomly like this, which looks like a chaotic orbit. But you also have regular orbits here. And at the center of this, you have this. So this is, by the way, the shape of this. So it almost looks like a circle, but it's not a circle. It's got a very rich collection of orbits. one of these chaotic blue orbits will be looking like this in the XY space. Here at the center, you have the simple periodic orbit, which is just bouncing back and forth. Here you have a periodic orbit which looks like a triangle. And then in the neighborhood of this stable orbit, it is in fact stable. If you go slightly away from that, you have these islands which are here. In the XY plane, it will be looking like this, quasi-periodic, and it's in this neighborhood of these. So all of these kind of orbits are there in the same billiard at the same energy. Okay, all this is at the same energy.
So this one for which billiard you say?
This one, Limacon, when epsilon is 0.3.
Why then you are showing the picture of the circle?
It's not a circle. See, epsilon is 1 looks like this, cardioid. So epsilon is 0.3, it's not yet, but it's not a circle. So that subtle non-circleness is sufficient for it to display this. It's not a sudden thing, so all of these things will be smooth. It's not like there is a phase transition kind of, or you can say epsilon is 0 is a phase transition. Except that the measure,
So you see that for any positive epsilon,
yeah,
which is, let's say, some form is looking like a triangle, but if I do it for a long time, you will see everything.
actually when epsilon is 0, I haven't plotted it here, but you will see that, no, epsilon is 0, let's start with the integrable case. For a circle, because angular momentum is constant, actually you will have, you'll have this to be, so the velocity at which it's hitting, because angles are all the same when it is hitting the thing. So the tangential velocity, the speed will also be the same. So you will have straight lines, segments here. And those straight lines get perturbed into these kind of things. You're talking about these orbits here, these triangles and so on.
Yeah, no, what is like this?
So this triangle, for example, in the circle, there will be a family of triangles, a continuous family of triangles. Now one of them will remain, others will be destroyed.
No, you're saying for any, but I thought for sufficiently small epsilon, you will have some regular structure.
You will have regular structures. So I'll come to another example because I didn't do
When you
this.
go from this regular to irregular structure, even in this 40%. So is it, you are saying it's not drastic, but then what does it mean?
Maybe I'll show you other examples where this will be more, otherwise I'll be just talking in words. But I need to make a decision at this point, but there are some.
So for the triangle,
Yeah.
the visually looks like it is hitting at the same tangential velocity. So it should just get horizontal lines, but it's not here.
Yeah.
Is it because of the slight cusp, the slight structure?
You're saying that the velocity is here
Yeah.
and here. You're comparing.
The triangular.
Yeah, between here, here, and here, you're comparing. Yeah, that will be the case. Because you see, this on this, it is just moving from here, here, and here. And this is like the velocity. So that's almost the same. Yeah. No. It's just to differentiate, otherwise everything will be looking in one color. The color, there's no. The blue is a single orbit. It's a single orbit and it's going around like this. Red are many orbits which are doing this. Okay, now let me show you more because by the way, I started at 3 o'clock. I go till 4:30, is it? Okay, so time for some. So this is the most famous example, the double pendulum. At low energy, 2 degrees of freedom. Normal modes, you can do analysis from your master's courses, find 2 frequencies. But higher energy, it's no more, it's far from, there's no normal modes as such, and it can behave in this well-known chaotic manner. If you guys haven't seen a real pendulum, it's double pendulum, it's time you did. So this is an example of chaotic situation. So the energies are quite different in this. You can see that the energy here is minus 27, here is plus 28. So this is an example of something which is chaotic. Here is another one which is displaying what does this chaos imply. For a practical purposes, one of the important practical implies so-called sensitive dependence on initial conditions. You start from two initial conditions, you are very close by. After a short time, they are completely separated. So to illustrate that, here I've taken this from the internet about a triple pendulum. Now, you will think that there is a single triple pendulum which is going by. So let's see what happens to this. So now, it's doing this dance. So there was not a single, but actually there were some 40 pendulums with slightly different initial conditions. They were following each other for some time till, it's a very short time by the way, and then it all breaks loose and there is no real correlation between these pendulas. So this is the hallmark of chaos. That is, it is bounded, things are not going off to infinity. At the same time, there is this highly sensitive dependence on initial conditions. All of these examples have this, but let's go back to an integrable system. We said circle billiard is integrable. We'll start off 5 particles which are very close by, so the angle is almost the same. And then as the bounces are growing, you will see that they also separate. It isn't as if they are always close by. They separate, but there is still a fair amount of correlation or synchronization between them. And the kind of growth of the distance between them is polynomial in time compared to what will be in the chaotic case an exponential. Okay, so this is the crucial difference. It's not as if non-chaotic or integrable systems don't have a dependence on initial condition. They do, but they are not sensitive enough. And their growth of these initial differences are polynomial in time. So let's go back to the stadium billiard, which, and then we will simulate the same thing, 5 initial conditions, in fact the same delta for this and that, same 5 initial conditions actually. And you can see that after a very short time, they're not even correlated like that. One is going as if they don't really know each other. So, so this is the illustration of sensitive dependence. And also every orbit is almost, going throughout there is no, like in a circle we saw there were excluded circles and so on. This one seems to be going to every point of the billiard. Okay, so now we are going to try to understand better what does this mean. And so I want to go back to one dimension. But maybe even before this.
So as you say that since it is bounded, they cannot go infinitely far away.
Yeah.
So what is the quantitative measure you will use for this system to distinguish chaotic versus non-chaotic?
It's a Lyapunov exponent. I'll come to that. But maybe I will decide to, yeah. Yes? Yes? That's the Lyapunov exponent. It's related to the Lyapunov exponent. I'll come to that. So, I just have to make a choice as to whether to go into this and then come back into some of these 2 degrees. Okay, let me follow what I have, because anyway I'm not going to finish the Bindu. Let me, let's try to understand this chaos a bit better. And I think that the billiards are too hard. Double pendulum is too hard, forget about the triple pendulum. So we'll go back. But before we go back, I want to motivate what does going back mean. I motivated that to study 2 degrees of freedom system is equivalent to studying 2-dimensional maps through the Poincaré surface of sections, and these maps are area preserving. So we'll come back to that area preserving two-dimensional maps. But before that, we will go even into one-dimensional maps. Why 2 dimensions? One-dimensional maps turn out to be rather simple. So what does one-dimensional map means? There is only one phase space variable. Let's just call that x. N is now discrete time. You have some function f. F of xn equals xn plus 1. And we iterate this. So the dynamics is simply xn plus 2 is f of xn, etc. Okay. Now it turns out that such a map is simple if this function f of x is monotonic in x. If it's constantly increasing or constantly decreasing, it's simple. And actually this is related to this Poincaré-Bendixson theorem which I discussed last time, because the surfaces of section of two-dimensional flows will be monotonic functions. Okay, so they are one-dimensional maps and they will be monotonic in general, not even if it's Hamiltonian or something. And therefore, it's actually quite easy for you to see why this is simple, why this is the case. If it is monotonic, f of xn is larger than, let's say that f is monotonically increasing, f of xn is larger than xn plus 1, and f of xn plus 1 is larger than xn plus 1, and so on. So it's just increasing monotonically, x itself is increasing monotonically. It can go to infinity or it can go to a fixed point. That's all it can do. So it's not that interesting dynamically, and therefore the most interesting maps to study, one-dimensional maps, are not monotonic. Non-monotonic maps have been studied since the 1970s very intensively, but even before that people knew about these kind of things. So here is a famous logistic map, which is, okay, I should have not put 4 here, but R. Okay, this is this parameter R. So this is just a parabola, R xn into 1 minus xn. It's nonlinear because there is an xn square here, and it is not monotonic. It's got a, and you're going to look at x only in the range 0 to 1. It's got a shape which I will show you in a minute. Now you take any initial condition x0, you iterate this in this map and you see what happens, and you have this very well known bifurcation diagram which happens as a function of this parameter R. This parameter R here, which unfortunately looks like 4 in my slide. So as this R is smaller than 1, all the initial points, any initial point you take will tend towards 0, will tend to the origin. And if R is greater than 1, it will tend to this 1 point, R minus 1 divided by R. And after 3, it will go into a period 2 cycle. And after something else, some 3 point something, it will go into a period 4 cycle, period 8 cycle. So it's called a period doubling bifurcation, series of bifurcations of this kind. I've shown this from 2.8 or something here. You can see more clearly this bifurcation diagram which is taking place here. So then a very complex set of orbits starts occurring here, and the very interesting non-trivial dynamics of this simple map. And at r equals 4, it's a fully chaotic system which we will study in more detail. So this is an example of a logistic map. It's called logistic because it's model for population growth. And if you don't know about it, there's a paper by R.M. May, a very famous paper from 1976, Nature, which talks about this. I think it was a paper that made this map most famous and led to a lot of development in nonlinear dynamics itself. Okay, so now let's see what happens in this logistic map. So here I've written this correctly. So Rx into 1 minus x. So what I'm doing here is varying R and f of x is being plotted. And what you're seeing in red is an orbit. You're starting from x0 and then you're plotting what happens to this. Unfortunately, I can't seem to stop it so that I can't show you this. But you can see that there are, as R is growing, there is this fixed point at the origin, which then becomes a fixed point here, which then becomes a period 2, then a period doubling bifurcation occurs, and then it goes into chaos. So R equals 4 is the most interesting point, and you can see that in this case this is the map. So you can start with some x0, and then you will have a bunch of initial, you will have some bunch of orbits, and then you have, if you change the initial condition, you will have a very different orbit again. So maybe we will see this more clearly in this sensitive dependence on initial conditions at R equals 4. So we'll fix R equals 4, and so all we are doing is iterating 4x into 1 minus x. We will start with some x0, and we'll start with another x0 which is away from that by 1 part in 10 power million, 10 power minus 6, and we will plot both the xn for both of them together. Okay, so that's what we are doing here. So I've started from 0.4 and 0.4 plus 10 power minus 6. So one is blue and the other is red. Unfortunately, this particular simulation which I have, it's disappearing, so you have to be really quick. And you can see that it's following each other for a time, and afterwards it's completely different from each other, the blue and red. So it's exactly like the triple pendulum case. There is a critical time till which they are following each other. First of all, it looks pretty erratic. It doesn't look like it's a simple, dynamical system, but that's the fun of chaos. The rules are simple, but then you have this. What happens if you decrease delta 0? So now you go to 10 power minus 10, same initial condition, 0.4. You can see that that time is being postponed. The time at which they depart is being postponed, and that happens. So you can, let's just go to 10 power minus 12. So it's still, it's not very far. 10 power minus 12 is very small indeed, but at a time of around 40 or something, 40 iterations, it's completely different from each other. Okay, so this is illustrating the sensitive dependence on initial conditions. Now, how do we, yeah. Not Hamiltonian, not even other, not even, you can think about them as not 1 degree of freedom, but yeah, I mean, I was going to say time dependent, but with 1 variable, not 1 degree of freedom. Not non-monotonic, that's what I said. If it's a genuine autonomous 2D phase space, it cannot be non-monotonic. It's always monotonic. No, for any. In fact, that's how Poincaré-Bendixson proved their theorem. By the way, a good source for Poincaré-Bendixson accessible to physicists is a book by Hirsch, Smale, S-M-A-L-E, and Divani. Maybe I will write it down at some point. But that has proofs of some of these things, not the KAM theorem.
So it's not very clear because the lines, but this after that they again appear randomly or towards the end.
I don't know.
Continuous line is just a set of points going like that, or
See, it's a discrete set of points. It's just being connected for visual thing.
but these points are what the real points. I mean, what I'm asking is that their positions are random or
Positions or random, which one? There's nothing random in the sense that it's all coming from the logistic map.
yeah, but random in the sense that random number.
Yeah.
Is it random in that sense? X for suppose
You're asking if we do some random number tests, will they turn out to be positive? I guess so, but it's you have to be careful because actually random number generators do use maps like these, modulo maps, but with very large multipliers. So not 4 and so on, very large multipliers. So yes, so here correlations will be decaying. These are deterministic chaos systems. So yeah, I mean they appear random. So they will be random in certain sense. I will come to in what sense they are random. Yeah. It's the difference between the two initial conditions. So you're starting from point 4, that is the red, blue, and the red is 0.4 plus delta, 0. You're starting from 2 initial conditions. I want to show the sensitive dependence on initial conditions. Okay? All right. Yes, it depends on delta. It's on the slide. So, very simply here, okay, so now let us define something like this. So you have an initial difference between two orbits, 2 points. That's the initial condition. Delta x0 is the difference between the two initial conditions. And after time n, let's say that their difference is delta xn. So let's take their ratio and the modulus of that, because we don't care if one is the negative or the other, we are just interested in the absolute values of these things. And we are going to see whether this is exponentially growing in this time n. So to do that, we will take a logarithm of this and divide by this time n. N is the same time n. And if you do this for finite time, you'll get some number. The actual Lyapunov exponent, and this will be called a Lyapunov exponent, corresponding to this initial condition x0, is defined by these two limits. Limit as delta x0 going to 0 first, and then the limit as time goes to infinity. Okay, so this is the double limit defines for you this Lyapunov exponent. For one-dimensional maps, it's very simple, because what is this? Delta xn divided by delta x0 is just a product of the derivatives at that point. Maybe I should write here something, because as Dibyendu said, I have to write. Shall I turn on the light? Okay, look, it's rather simple, and it's important because it just generalizes to higher dimensions in this way. So let's look at this. So this is f of x, and our dynamical system is xn plus 1 is f of xn. So we start from x0, we iterate this, f of this, f of that, and keep doing this, and we get the xn. This will give you x3. So now, if we start from 2 points which are close by, that is delta x0, in one iteration, how far are they going to get? So they are going to become equal to this delta x1. And as delta x0 tends towards 0, so delta x1 divided by delta x0, what is that going to be? That's just the ratio of this to this. On this triangle, the ratio of this to this, and that is just the tangent to that. So that is f prime at x0. Okay? So this is a multiplier. This f prime, the derivative, is telling you how far away it's being pushed. F prime is larger, it's going to be pushed away more. F prime is small, it's not going to be pushed away. Okay? Now that is in one step. Then you have gone to x1. So this x1 has come here, and then it's going to now become, so this is delta x1 is going to expand again, but now it's going to expand by a factor of f prime of x1. It's going to expand by f prime of x1. Expand or contract is going to change by this. And therefore, this delta xn divided by delta x0 is just the product of these f prime xn dot 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 f prime x0. So product of the derivatives, and the log of that is therefore the sum of the log of that is the sum of the logarithms something like that. Okay, so that is precisely what I have written down here. It's the log of the, so it's the average of the log of this. And why do we have the f prime? You see, because we have taken this limit first, delta x0 tending towards 0. That's why it becomes the derivative, exactly the derivative. It's a tangent map. Okay. If we did not do that, this will not even be a sensible number. I'll come to that in a minute. But this is just the time average. If you think about this as a time, this is the time average of this. So you can expect that this is a well-defined quantity, some time average. And for the logistic map, the derivative is easily calculated. It is this, r times 1 minus xj. So I will encourage you to do this for the logistic map, for the students who have not done this before. And then you will get this interesting curve as a function of this r, the Lyapunov exponent. So you see that if the Lyapunov exponent is negative, it means that this delta x0 is tending towards 0. Okay, it's not chaotic at all. Orbits are attracting; they are coming towards. Whereas if it's positive, then it's exponentially deviating from each other, and you have sensitive dependence on initial conditions. Okay, so you have this very complicated phenomenology which is going on here, and at r equal to 4, you have this very nice value for this Lyapunov exponent, which is equal to log 2. This is exact analytic. At r equal to 4, it is logarithm of 2. Okay, so your question about the time scales is just coming here. So now if we know that this exponential, there is a growth by this exponential growth with this lambda, if you take some initial delta 0, your final delta n is going to be growing like this, with lambda being the Lyapunov exponent. And therefore, the time scale when the difference delta n becomes order 1, which is your entire phase space, that is the time scale at which, that's a critical time scale, and that is the Lyapunov time scale, which will be log of 1 by delta 0 divided by lambda. So in all those simulations which we saw, that's why if you go twice in order, you cut down the error by from 10 power minus 6 to 10 power minus 12, you will be getting a doubling of the time. That's all you will be getting. This because of this exponential behavior in this lambda. Okay, so this Lyapunov exponent also answers actually, Sanjeev, the question about you have a finite phase space, you have a finite orbits, it's not going to go to infinity. So the critical thing is to first take this delta x0 tending towards 0. So you're going to take orbits which are close by, really delta tending towards, you're going to take it on the tangent plane and then go. But also it's important to emphasize that the Lyapunov exponent is an infinite time quantity, because when we look at quantum, there's a lot of quantum literature where they're doing small times and they're talking about Lyapunov exponents. Yeah. Yeah.
So for quantum system, we call something called Fowler's time.
Yeah.
Actually related?
Kind of. They are related. I'll come to that. It's an interesting question. This is basically what we will call in single particle. Fowler's time is more for multi-particle system. You will have something related to h bar there. So this is actually more like the Ehrenfest time, rather than, I don't know, the Thouless and the Ehrenfest, similar, yeah. So this is more like the Ehrenfest time, and the delta 0 here, there is no delta 0 meaning, because there is a meaning, but there is no fundamental meaning to that, because I can take 10 power minus 100 I want, and I can ask my, classical there is no limit, but in quantum there is a limit, and so that will come, the h bar will start playing a role in this delta 0. Okay, is that clear? Yeah. Very good, thanks. Yeah, I would have missed that point. There is a dependence on x naught, right? But for a chaotic system like this logistic map, it will be almost washed out. So whatever may be your x0, this value will be independent of x0. There may be still a measure 0 set of points where this is not true. For example, for the logistic map, the simple 4x into 1 minus x, this is log 2 for all orbits except the fixed point at the origin. Left as an exercise, find out what it is at the origin. It's very trivial, it's very easy. All you need to do is take a derivative and put x equal to 0.
What these sharp chips, they are in any way related to the inequality?
Yeah, because you saw this in this bifurcation diagram, this complex set of windows, sudden windows. So the famous thing is this period 3 window. So suddenly you will have stable things, right? So it corresponds to those kind of stable windows. But maybe actually it's worthwhile saying this here, Anna, because I want to emphasize the following fact. This is a famous diagram in almost all books on nonlinear dynamics. But one thing it does not show is the following. Here I said that there's a fixed point here, and then this becomes the fixed point. It's not as if this fixed point has disappeared. That fixed point has become unstable, and you have a new stable fixed point. So here also, this orbit is coming here. It's not as if it's disappeared. It's just becoming unstable, and these two are stable. So unstable, stable. So actually, at this point, it might look like there are only the 3 stable orbits, but actually there are a whole host of unstable orbits. And what happens at r equals 4? You have only unstable orbits and unstable periodic orbits. I'm not talking about non-periodic orbits. So chaos, I'll come to that. That's an important characteristic of chaos. But at this point, the x0 dependence, so people talk about Lyapunov exponent of a system. So by that they mean typical orbits, and almost all orbits will have that Lyapunov exponent. But you can find isolated orbits with a different Lyapunov exponent.
But people also talk about Lyapunov spectrum, right?
Spectrum, yes.
So those points will take care of.
No, that is just because you're going to higher dimensions. You have one-dimensional map, we'll come to that. One-dimensional map, you have a 1 Lyapunov exponent. You have n degrees of freedom. You have a 2n flow. For a Hamiltonian system, you'll have 2n Lyapunov exponents, because you'll have 2n directions in which you can have this tangent direction. And basically, yeah, I'll come to that later. Okay, so why is this thing solvable? Why is r equal to 4 is a solvable point of the logistic map, although it's also fully chaotic. So we can solve it in this very simple way. Xn plus 1 is 4xn into 1 minus xn. We'll substitute this xn as sine square pi theta n, okay, into this, now trigonometry. So that's the definition of theta n. Sine square pi theta n plus 1, that's the definition of theta n plus 1, is 4 sine square theta cos square theta. So now we go back to trigonometry classes, and 2 sine theta cos theta is sine 2 theta, and therefore we get sine square 2 pi theta n. So it's crucial that there is a 4 here, and you get sine square 2 pi theta n. So by comparing this, you have a simple map in this theta n variable, which is theta n plus 1 is equal to twice theta n, except that there is no, this is all within the sign, so you have to put up modulo 1. It does not, more than 1, this thing has no meaning. It wraps around on the circle of perimeter 1. So there is the sine square pi theta n has a period of 1. Theta period is 1. Okay. So now this is called a doubling map. We will call this a doubling map. It is even more simpler than this. It looks linear, twice theta n, but it's not linear because of the modulo 1 condition. What is modulo 1 condition? For those of you who have forgotten or don't know, modulo means you subtract or you add an integer so that the result lies between 0 and 1. It's winding around a circle of perimeter 1. So theta n plus 1 is twice theta n if theta n lies between 0 and half, because then twice theta n will be lying between 0 and 1. You don't have to do any subtraction. But if theta n is lying between half and 1, twice theta n lies between 1 and 2, and therefore you have to subtract 1. So this is the doubling map. We'll call this doubling map. This can be immediately solved for theta n in terms of the initial theta 0 like this. Twice to the power of n theta 0 modulo 1. And therefore we can put this back in here and solve for xn. So we can solve this logistic map in the sense that given an initial condition x0, I have a prescription for jumping immediately to what happens at time n. This is what we will call a solution, right? And it's given like this. So that looks nice, but actually it's an important example for two reasons. One, I want to emphasize that analytical solutions are completely compatible with chaos. Chaos is a dynamical property. It doesn't have to do with our ability to solve or not. Typically, it coincides with our ability to solve, but which is fairly minimal. But in this case, it illustrates that you can completely solve the problem according to analytical things and be happy. But it's of no use because we haven't understood anything by writing down a solution of this kind. Yeah. No, absolutely not. Solvable chaotic system if you want, not at all integrable. What do you mean? Because it has no other constants or anything of that kind.
But it's exactly solvable. Sometimes it could be
Solvable, that's what I want to emphasize. I want to emphasize that solvable chaos does not mean that you can't solve it.
But I'm saying that is solvability is the same as integrability?
No, I did not say. In fact, most integrable systems I can't solve. There may be integrable systems. There are, in fact. You can't solve them in this sense. For example, I'll say even take x power 6 one-dimensional potential, right? There are no special, you have to define a special function to solve that. It's not analytic functions or anything of that kind. So no, solving is one thing. Solving in this sense of writing it in terms of known functions is one thing. Chaos is another. Non-integrability is another.
Modulo 1 is not important for it, no? Because you are anyway going to.
Not important for what?
I mean, I can say that theta n plus 1 equal to 2 theta.
But
Theta to whole space without hurting.
yeah, it is not important for this particular solution, but it is it is very important.
I mean, I don't have to restrict theta between 0 to 2 pi, right?
I'll tell you, well, actually what technically this map here is a mapping from x to theta space, and you can also go back, but in fact given a theta you can go to x, but from given an x you'll have two values of theta. So this is actually a conjugacy, and it's a semi-conjugacy of some kind. But why I want to emphasize modulo 1, and as we are going by, this is a doubling map, is that every orbit in x will have an orbit in theta. Like if you have a periodic orbit in x, you'll have a periodic orbit in theta. If you don't put a modulo, you don't have any periodic orbits, except at theta equal to 0, which is a fixed point. You won't have any other periodic point. So modulo is very important. So now, although we have solved it, we will really understand it by this following approach. Now we will understand the doubling map. Okay, theta n plus 1 is twice theta n modulo 1. By expanding in binary this theta 0. So binary expansion is 0.a0, a1, a2, where a's are either 0 or 1. And binary expansion is given like this, 1 over 2, 1 over 2 square, etc. Okay. Now, let us put this theta 0 and find theta 1. Now, if theta 0 is less than a half, what is the value of a0? A0 will be 0 if this is theta 0 is less than a half, because if this is 1, this has to be larger than half. So a0 is 0. Okay. Now, twice theta n is just multiplying by 2. So you will get a1 by 2, a2 by 2 square, etc. Is that fine? Because a0 is I can do this whole thing in one step. Let's just multiply by 2 theta 0. So this becomes a0 plus a1 by 2, etc. Now a0 can be 0, in which case it won't appear here. If a0 is 1, it will also not appear, because in that case theta 0 is larger than a half and I have to subtract 1. Okay? So a0 disappears from this picture and theta 1 is 0.a1, a2, etc. Which one? A0 is 1. Yeah, theta 0 is 0.1 something. It's not less than half. 0.1 something need not be, is not less than half, because there is 0.1, everything else is positive. This is already half. If you take a number which is larger than half, binary expansion, its first most significant digit is 1. So that is what that is. Is that clear? Do it. And therefore this theta 1 is just given by this. And what will be theta 2?
So why are you doing by the binary logic basically? Is there any reason for that?
Of course, yeah, I'll come to that. What is theta 2? Huh? Huh? No, it's not just double. It is 2 theta modulo 1. So, but in binary expansion, what is theta 2? Yeah, it's a bit shift, and it is a2 by 2, a3 by 2 square, etc. So you see, what is happening is actually a very alarming thing. You are given a binary number, you're given a number in binary expansion. These numbers determine for you finer and finer that number, how accurate your number is. As you are putting it through this deterministic map, you are exposing the most significant digits you're throwing off. You're just deleting a0, deleting a1, deleting a2 in the next step, and so on. So if you knew this till 10 power minus 6, that is a precision of 1 by 2 power 20. You know 20 bits. Then if you put it through this map for 20 time steps, you don't know where you are. You have reached your level of ignorance. So this is precisely the Lyapunov exponent and the Lyapunov time. And you can see that the 2 is coming from that. So this is the, so here I've given an example. Theta 0 is 0.171. That is the binary expansion. So it's just called a left shift dynamics. So the dynamics is that of a left shift. It's taking this point A0, A1, A2, left shifting this and deleting this A0. So Dibyendu, if you take this in any other expansion like 10 or something, which would be for decimal, it won't be like this. But there will be a simple map for that. That will be 10xn modulo 1. If your map is 10xn modulo 1, then just normal decimal will work for you. Because it is too, yeah, then it is most clear what is happening in the dynamics. This is the left shift dynamics. Yes. I did not calculate it, but it's actually very obvious from here that it is log 2. That is, I just stated it, but here you can see that for theta 2 theta n it is log 2 because the derivative of 2x is just log, is just 2, and the log of that is, it is not changing with position, and therefore it is log 2. Absolutely, yes. It has to do with the same thing. So the dynamics on this is a left shift which you won't see from this solving that. And it is completely clear, and it is also alarming, and you can see now all the sensitive dependence on initial conditions and so on. Let's take 2 initial conditions. Sure, it's already 4:30. I'll just maybe finish with this particular point. Because you can use this binary expansion to do many things. Very simple. Let's take an x0, which is 0.a0, a1, an minus 1, and then some an, okay, and an x0 tilde, which is 0.a0, a1, it matches till n minus 1, and then it differs. Let's say an tilde, it differs from this. What will be the difference between these two? It will be smaller than 1 by 2 power n, because it's matching all the way till 1 by 2 power n here, right? The difference between these will be starting from 1 by 2 power n plus 1. So this is smaller than 1 by 2 power n, but now,
N plus 1, right?
it could be n plus 1. I mean, I'm just saying it's, yeah, smaller than that. You want to put n plus 1 here? I'm happy if it increases. So now xn, what happens to xn minus xn tilde? This is 0.a, a1, so an minus, so this is just some two random numbers, two numbers which need not have any connection to each other. One can be as large as 0 and the other can be as large as 1. So this is of the order of 1. So in this time n, you have lost n bits of information. So that is sensitive dependence on initial condition, because in a polynomial time, you have lost a delta of which is exponentially small in this 2 power 1 by 2 power n plus 1, right? Your initial delta, which was some 1 by 2 power n, and then there is some time which you are, so this is delta times delta 0, so this is delta 0 is 1 by 2 power n times 2 power n. So this is your, that is your expansion. At each time it's undergoing an expansion of 2 power n, it's becoming of the order of 1. So yeah, so that shows the sensitive dependence on initial conditions. You are seeing that, and actually in all the more complicated cases, you're having somewhere something like a left shift going on in the phase space, although it will not be so obvious at all. Okay, so
Consider for the more general classical models where theta n plus 1 is p theta n mod q.
mod q.
Yeah. The coefficient is p and the mod is some other q.
Hmm.
Is it generally this will be some theory for general p and q?
Yeah, it will, provided your p is larger than 1. It has to expand. So what is geometrically what's going on? What is this 2x modulo 1 geometrically? You're taking a unit interval, twice is elongating it by a factor of 2, like you're stretching it, and then modulo 1, you're folding it back. So it's important to stretch for this sensitive dependence on initial condition and instability. So if this is less than 1, you're contracting, that won't help. It has to be larger than 1, it has to stretch, and then you have to fold back. The folding is just given by a modulo, and that modulo, whatever you're doing, that's okay. That is only determining for you that final length. Okay, so that stretching factor is determining for you your Lyapunov exponent. So if you stretch by p, log of p is your Lyapunov exponent. And all of them are chaotic.
There's some map that discusses pizza stretching and folding, right?
Baker's map. This is Baker's map in one dimension. I'm calling it a doubling map, but this is precisely the action of the baker, or when you're making chapati and so on, you're stretching, folding, stretching, folding. We'll see that. I should have done all that in 1 hour.
That's the basic random number. P
Yeah, I think with very large P and then,
normal then.
yeah, yeah. It uses something like this. It's a pseudo random number generator. So these are, so but yeah, the point is all those kind of things are behind all these unstable systems and yeah, um, behind chaos. So it's looks like the ingredients and definitions of chaos have to wait a little bit. So I'll be talking about definitions of chaos. What exactly is a definition of chaos? And then I will talk about forced oscillators and about two-dimensional area preserving maps. And here is a Baker, by the way. So there is an area preserving version of the doubling map, which is called the Baker's map, and there are also variations of the Baker's map. Okay, all of these things, our agenda is really quantum mechanics, and we'll be doing quantum mechanics of all of these things: the Baker's map, the standard map, the kind of kick pendulums, and so on. But one-dimensional maps are useful for us to develop the, I think, the kind of understanding which is, it doesn't require very great mathematics, but I think we can understand. For example, I think you'll agree with me that the left shift can be taught in high school, multiplication, and but that's really the heart of chaos is left shift. All right, so I think I should stop here. Thank you. Devendra, you want to see if there are any questions in the...
Yeah. Is there any other question in the audience?
Also in the YouTube.
Yeah. When you define the Lyapunov exponent by the two different limits like delta x naught going to 0 and n going to infinity, so the end limit, the time goes to infinity, becomes an infinite sum. So how we can determine always that there will be a Lyapunov exponent when we have chaos? I mean, how will assert that the limit will converge to some exponent like lambda?
It's not, it requires proof.
Yeah.
So in fact, that's what Lyapunov did.
Okay.
In general.
So,
for general flows, he showed that this limit exists.
Okay, always.
That's why we are,
Okay.
Yeah. Yeah.
Okay, thank you.
And in these cases, you will see why that limit exists, because it's some kind of an average.
Yeah.
It's bounded.
Yes.
It's some kind of an average. And this average can exist if, I'll come to that. There is, yeah, in a sense, each of those things is well defined, and therefore the average is highly likely to be well defined. You have a bunch of numbers which are well defined,
Okay.
Except maybe going to infinity at one point, but that will be sets of measure 0. So when you can, you can average out over these things, those exceptional points will not be important. Average will exist.
Okay. Okay.
Yeah. But the average can depend upon that x0, your initial point, and so on. That's not obvious that it's not. Yeah.
Is it possible to have some Hamiltonian model behind such simple logistic map like this one?
For the doubling map, which is somewhat related to the logistic map, there are some attempts by a person called Divani. You can look at, there's a very nice book also by him, Introduction to Dynamical Systems. They try to fit in, but most realistic things won't be having something as simple as this, of course. But the important thing is that geometrically, this stretching and folding action, which you see, that is there in generic chaotic systems around what is called tangle. So the tangles, this is the chaos around a tangle. So yeah, it won't be as simple as that. This is for us to understand the essence of chaos. Yeah.
Any other question?
So I just want to clarify some this. So there are words like chaos, solvability and integrability, right?
Hmm.
So, so integrability is, I think, is Liouville Arnold
At
integrability.
least I defined it.
Yeah.
Yeah.
And solubility is something that's my ability of solve things or something like that.
Solubility is writing down
Some
the solution in terms of some known functions.
Yeah.
Yeah.
And so, and chaos, like when will I say it's chaotic?
We haven't come to that.
Okay. So if it's not integrable, can I say it's chaotic?
Not really, but that's kind of what I've been implying so far. But if it's not integrable, it can be a combination of chaos and integrable in the same system. So chaos will need a more formal definition, but for all practical purposes, sensitive dependence on initial condition is taken as a definition. So you can very roughly take, we have defined already what is sensitive dependence, at least I've given you examples and so on. You can say that if there is a positive Lyapunov exponent, it is chaotic. But at the same time, Sanjeev was saying, why put a modulo 1? If you put 2x, then that will also have a positive Lyapunov exponent without a modulo. Or you take an inverted harmonic oscillator, minus x square potential, it will have positive Lyapunov exponent. But you wouldn't call these chaotic. You would only call this unstable. So that's why I said roughly. Positive Lyapunov exponent is an important ingredient. Along with that, if you require that the dynamics be constrained within a bounded region of phase space, then it is as good as a definition of chaos. But there are other very important things I'll come to.
Thank you.